Ladies and gentlemen, welcome to Physics Rocks. It's true, it is the final lesson in the A2 physics series. We are going to take a look tonight at conservation of certain quantum numbers in order to explain the phenomenon of beta decay and beta plus decay. Once we've done that, we'll then figure out that this is actually better represented in Feynman diagrams. So we're going to dip our toes into how to do a Feynman diagram. So let's get started. In our last lesson, we took a look at these concepts here, the baryons and leptons. Leptons, being fundamental in their nature with no underlying structure, had lepton number 1 or -1 for the anti-lepton and 0 if you weren't lepton. Baryons, on the other hand, are composed of 3 quarks, and therefore if you are a baryon, you have +1. If you are an anti-baryon particle, you have -1 baryon number, and if you're not a baryon, you have 0. And we can pretty much sum this up in a few tables for some common systems. So for baryons, for example, we have the proton and the neutron. They are baryons of +1 and +1. We can have the antiproton and the antineutron, which would have baryon numbers of -1 and -1. The proton has a charge of +1, the neutron a charge of 0, relative to the proton, of course. Something that you've learned probably since about 3rd year, I would imagine. But notice that our proton or neutron have lepton number of 0 because they're baryons, not leptons. And our electron here has a charge of -1, a baryon number of 0 because it's a lepton and hence has lepton number of 1. Technically, it should be lepton number of +1. I should add that in just for completeness, so we'll put a plus there. Okay, now if we were to then take a look at our leptons in a table, we could have a table that looks a little bit like this. That we have particular leptons. We have the electron and its antiparticle, the positron. The electron has a charge of -1, and the positron, being the antiparticle, has a charge of +1. Baryons have 0 and 0, and the electron has a lepton number of 1, and the positron a lepton of -1. Again, that should be a plus in there, so we'll copy this little plus across. Not that it matters, like 1 is positive, but we'll make it nice. Okay, now down here we have the neutrinos and the anti-neutrinos that are associated with the electrons. So this is our first generation. For those of you who are doing a little bit of extended reading, you'll know that we have the 2nd generation muon and the 3rd generation tau, and then they're associated antiparticles and their associated neutrinos. But we're going to look at 1st generation tonight. Okay, so electrons and positron. The electron is the lepton, the positron the antiparticle of that with charge here. The neutrinos that are associated with those then are the electron neutrino, which has a charge of 0, a baryon number of 0 because it's not a baryon, and a lepton number of +1. And the electron antineutrino has charge 0, baryon number 0, and lepton number -1. So, all right. Night mode recommended by Jericho. Okay, yeah. Hello, Wencha. I see you there. Hi, Matthew. How are you? Started early? No, I think 9 o'clock, didn't I? I think I said 9. Maybe not. I literally started at 9 o'clock, so we're all good to go. Okay, so these are our particles here. We've got a couple of baryons here. We've got a couple of leptons going on over here, and we're just taking a look at their numbers. Now, the numbers that we're going to look at tonight, the quantum numbers that we're looking at here are charge, baryon number, and lepton number. There are other quantum numbers associated with things. Okay, there's things like spin quantum numbers. We're not going to take a look at those tonight. These 3 will do us. Okay, because they are conserved throughout any reaction we want to take a look at. Now that's a conserved property. We know that momentum, for example, is conserved, provided no external forces act. We know that energy is conserved in a closed system, and this is conserved, and these quantum numbers are also conserved. So this gives us a way of predicting and building models of what will happen in future. Now, of course, our baryons themselves, since they're made of 3 quark structures, can then be broken down into their quarks. And we're going to take a look at our 1st generation quarks, so that is the up and the down quarks. Okay, so we're not going to look at charm, strange, top or bottom, but they broadly play the same game here, just with different masses. So the up quark has a charge of +2/3 and a baryon number of +1/3, which makes sense because you're going to need 3 of these to build a singular baryon. The anti-up has baryon number -3rd and charge -2/3. And then the down quark negative a third for its charge, and baryon number plus a third. I just see Matthew in chat saying, it seems your last lesson of year 14. Want to try a Zoom once the lesson is over? Yeah, nice of you to send me the password this time. You invited me to a Zoom quiz last week, sent me the code, but didn't send me the password. I took it seriously personally, cried myself to sleep. The down quark has a charge negative a third, the anti-down plus a third, and so forth. Okay, all of these, because they're not leptons, have lepton number of 0. Okay, so keep that in mind when we consider any particular reaction. So let's take a look at a standard reaction. Let's try something like an alpha decay. Okay, so an alpha decay is a relatively straightforward concept. All right, let's imagine that we have some nucleus X with, let's give it a mass number and an atomic number. So let's give it a mass number of 240 and an atomic number of 135. I'm not even sure what that is. Somebody can look that up. Okay, 135, 240. Okay, and let's have that alpha decay. So that's going to undergo an alpha decay. Now, because it's going to be an alpha decay, it's going to change what it is, because it's going to change its atomic numbers. It's going to become material Y. And it's going to lose an alpha particle. So let's get ourselves a little alpha over here. There's our alpha particle. And we know that an alpha particle has a mass number of 4, and it has an atomic number of 2. That's the wrong font, but it'll do. Okay, so this is a standard alpha particle system. And we'd previously taught you this as being the conservation of mass number and the conservation of atomic number. But what we're going to take a look at here is we're going to take a look at charge, baryon number, and lepton number. Okay, and we'll call that Q for charge, because that's what we should be doing. Okay, so our left-hand side of the equation and our right-hand side of the equation should add up to be the same thing, we hope. Now, we're dealing with just nuclei, but let's assume, we can assume if we want that we're, that should be a 133. That's better. So total charge on the left-hand side of the equation is 135. Okay, relative charge units, so compared to a proton, because there's 135 protons. Agreed? And then we've got 133 charges there, plus 2 charges there, giving us a total of 135. So we can happily state that, in this case, charge is conserved. Good news. Okay, baryon number, right, we've got to take a look at how many baryons there are. Well, there's 135 protons, there's 105 neutrons. We can do that with the difference of the two. Each of those has a baryon number of +1, so we can just take the mass number. So the baryon number here is 240. That's grand. The baryon number here is, why did I not change that earlier? That should be 236. Keep up with my chat. That's 236, and then plus the baryon number of the alpha particle, which is 4, 2 protons and 2 neutrons. And then that should equal 240. Of course it does, because it just made it equal 240. And that means that we have conservation of baryon number here. Now we're going to assume that we're simply dealing with a nucleus here, though we could count electrons, but we're not going to. So the number of leptons on this side, well, is 0, because we don't have any electrons in the nucleus. We have no electrons in the nucleus there, and an alpha particle is a helium nucleus, giving us a total result of zeros all round, and we have conservation of lepton number. Yay! Okay, this is like the least interesting thing you've ever done, because this was an equation that you learned in 4th year, and all the physics you did with it was just top line adds up, bottom line adds up, move on. Yep, happy enough with that. So let's take a look at how this operates in a slightly different arena. Let's try it with beta decay, because the game gets interesting here. So in beta decay, what we have is we have a particular material of X. Let's give it a mass number of 198. Why not? And let's give it an atomic number of, let's try 94 for the funds. Well, that's unlikely to undergo beta decay, but never worry. That's going to undergo beta decay, so we're going to get our little beta over here. Oh, not a capital B, a small beta. And we want to give that its normal concept. So beta has a mass of 0 and a charge of -1, because it's an electron. Right? And you know what? Rather than call it a beta, we're just going to take that little beta out, if I possibly can, and we're going to call it an electron. Because our later explanation will probably benefit from us understanding that it is, in fact, a high-speed electron. That's what a beta particle actually is. This will, because we've got a change of atomic number, again, we've got a change of material. We'll call it Z, actually. I don't want any confusion with it being Y from last time. So what happens is a proton becomes a neutron turns into a proton. So our mass number remains the same because we've got the same number of nucleons. But because we have an extra proton, we now have 95 up here. Okay. All right. So this is our equation that we want to play with. And again, we will have our list of quantum numbers. We want quantum number Q, quantum number B, and quantum number L for charge, baryon number, and lepton number. So on the left-hand side of the equation, we have a charge of 94. And on the right-hand side, we have a charge of 95 and -1. And 94 is equal to 95 plus -1. So we have conservation of charge and everything is okay. For baryon number is basically the total number of protons and neutrons. So we have 198 protons and neutrons on the left-hand side, and that has to equal 198 plus 0 on this side, and that's fine as well. So we have conservation of baryon number. Good news. Now we go to lepton number. At the bottom here, again, we're going to assume that we have a bare nucleus here. So we've got a completely ionized piece of material, though we could have it as a regular atom, and feel free to do that. We have no leptons on this side, and that is, of course, going to equal no leptons on this side, plus a lepton, because the electron is a lepton. And that's a bit of an issue, because we now don't have conservation of lepton number. Okay, are we happy enough with that? So here we have a violation of the concept that I've literally just introduced to you, which is that these quantum numbers are conserved. And that's an issue for this equation. Okay, and the reason it's an issue for this equation is because this is not correct. Okay, this equation is wrong. We've given you this equation, we've let you answer it in exams, and we've told you it's right, but I'm afraid it's not, because lepton number is going to need to be conserved here. Now, it is true that we have no leptons on this side. It is true that this contains no leptons, and it is true that this is a lepton. So we need to balance this equation. So as a result, we're going to need another particle here that has lepton number -1. Okay, we must have that in order to conserve lepton number. So I'm going to go up to my little table of leptons here, and I'm going to find myself the leptons that have -1. So that gives me, I have the positron available, and I have the electron anti-neutrino available. Okay, now if I pick the positron, I could put that in. That will solve my lepton number problem. Okay, so E plus. If I put a positron in there, that works quite well, but unfortunately, I then have a violation of charge because I've added an extra positive charge in here. I would then break conservation of charge, so I can't use the positron. But I can use the electron anti-neutrino, which has no charge, so I can put a +0 on there, and that doesn't change anything. It is not a baryon, so I can put a +0 on there, and that doesn't change a thing. But it does have a lepton number of -1, which is exactly what I want here. Okay, in which case, I can add on to the end here an electron anti-neutrino. An anti-neutrino or a neutrino has the symbol nu. An electron anti-neutrino is a nu with a little subscript E attached to it, if I can get the font right, which is surprisingly difficult to do. And because it's the anti-particle, because that's an electron neutrino, we have a little bar over the top with a little minus on top. So we have the electron anti-neutrino. And this is the equation for beta decay. But if we actually want to describe beta decay correctly, we have it as material X goes to material Z plus an electron plus an electron anti-neutrino. All right. Ah, hello, Nicole. Oh, that's lovely. Thanks for suggesting that somebody would have to be somewhat intoxicated to suggest that they actually like me. But cheers, Matthew. It was true for my wife, I suppose. So you're probably spot on. Okay, now what's actually happening inside beta decay is not quite the case that a neutron is becoming a proton. Whilst that is true, we can do a little bit better than that. We can now look at it in terms of quark structure. That we have a neutron is going to become, here we are right here, it's going to become a proton. It's going to become, along with that, a little electron and an electron anti-neutrino, which is essentially massless. Well, it's not entirely massless, but it's so close as it makes no difference. All right, so to make ourselves a neutron, we need to build 3 quarks. 3 quarks put together that will give me a baryon number of 1 and a charge of 0 from our up and down combinations. Okay, so to do that, we will want to have an up quark for our plus 2/3, and then we will need a down quark, and then we will need a down quark. Agreed? Because up is 2/3, down -1/3, so 2/3 minus 1/3 minus 1/3, and then all of these give 1/3 plus 1/3 plus 1/3, which gives me baryon number of 1. So I've got up, down, down for my little neutron here. That's going to turn into a proton. Now, a proton is a little bit different. It is an up quark, and a down quark. Just satisfy yourself that that's correct. That up, up, down is a proton. 2/3 plus 2/3 minus 1/3 gives 1. Electrons are, of course, leptons and don't have an underlying quark structure at all, so they can just go over there somewhere. And our proton, our little electron anti-neutrino, also is fundamental. It's a lepton, so we can ignore it entirely as well. So the process that's happening here appears to be, well, there's an up quark and there's an up quark, so that's fine. And there's a down quark and there's a down quark, so that's fine. So what's really happening at the quark level in beta decay is a down quark is being converted into an up quark. And in the process of so doing, it's going to produce an electron and an electron anti-neutrino. All right, Americans have a rubbish sense of humor, Jamie. That's the problem there. Okay, so let's write this as quarks. Rather than writing it as neutron goes to proton goes to this, we could write it as, in terms of quarks, we have the down quark becomes an up quark plus an electron plus an anti-electron neutrino, which takes far too long to write, but we'll have a go at it anyway. And that is the quark equation for how to do beta decay. But it's not really what's going on. Okay, because how does this happen? What is the mechanism by which this happens? And for that, we're going to take a look at our bosons, our force carriers. Right? And what's happening is this. We have our little down quark. Okay? Our down quark will then split and become an up quark, which is fine. Right? And it will release a force carrying particle that is a W minus boson. And now remember we said last time bosons are force carriers, and the W minus one is the one that's responsible for the weak interaction. The weak interaction is what's going on in beta decays, both positive beta decays and negative beta decays. So we get a W minus boson created. The W minus boson, as you might remember from last time, has an extremely short range, right, and decays quickly. Okay, so this is carrying energy, but that energy is going to manifest itself as particles, and the particles it manifests itself as are, as you might imagine, an electron, and I'll just grab this from up here if I can. No, I can't. Dang, should have thought ahead. And an anti-electron neutrino. or electron anti-neutrino, I should say. Okay, which is U subscript E with a little bar across the top of it. Okay, so this is the process that's actually occurring. Down quark decays to become an up quark, releases a W minus boson. That W minus boson then decays to produce two particles, an electron and an electron anti-neutrino up here. Okay, and this process again has a conservation of lepton number and a conservation, but doesn't have conservation of charge because the charge went to the up quark. The extra +1 went up there. Is that all right? Okay. All right. Happy? I have no idea what you're talking about, Llama Llama, but I don't know. I genuinely don't know. I'm not on Twitter because Donald Trump's on there, and therefore it would be sensible to not be. Okay, I don't do social media either because I have no friends. So onwards we go. We would like to then express this in a diagram that's not just this horrible. Okay, because that's awful. You hand that to somebody and they go, what is that? Okay, so we're going to express it in a Feynman diagram because Richard Feynman is a far better physicist and a far better physics communicator than I could ever hope to be, and he came up with this process. Now, there are lots of different ways to draw Feynman diagrams. The way I'm going to introduce to you is what I think to be the simplest way, and it is a two-axis system. Okay, on the y-axis, we have time. On the x-axis, we have position. Now, this is Position for position. This is not a graph. Okay, can't stress this enough. This is a diagram of what's happening to our system. And what's going on in beta decay is that we have a little neutron, and it's going to turn into a proton. We'll do the quark model soon. A little proton or a little neutron is going to turn into a proton and release an electron and an electron anti-neutrino. Okay, so we need some rules for these diagrams, and the rules are dead simple. That you have arrowed lines are particles. So an arrow heading upwards is a particle. An arrow heading downwards is interestingly not going downwards because that would be stupid because time continues to travel forwards. You don't go backwards in time. A downward arrow is an antiparticle. Okay, so we try to read from bottom. We always read from bottom to top. So we have an antiparticle is downwards, a particle is upwards in this diagram. And then anything that's not an actual particle is represented by one of these little squiggly lines. Okay, and this will be almost certainly some form of boson, some form of interaction. Okay, and this is how the interactions between particles are generally met. There are some rules that are things along the lines of that if a particle meets a particle, then you will have an interaction of some description. So you will have to have two particles and no more than two particles in a particular interaction if you want to try and do quantum electrodynamics, which is some fun summer reading for you if you're heading off to do interesting further studies. Okay, so let's get our particle in here. Let's start with our little neutron. So we have a neutron, so it's going to be represented by a line. Okay, and let's give it a position. It starts off somewhere in space and travels along. Let's assume that it actually stays in the same position. So it's just going to sit there and travel through time, which is what I'm doing right now. Just sat on a seat, traveling through time. I'm going to label that as N for neutron, which is sensible. That neutron is then going to become a proton. And that proton is going to change position. All right, it's not going to sit where it is because that proton has to move somewhere because of what's about to happen on the other branch here. But we'll talk about that in just a second. We end up with a proton out here. And again, our arrow is going upwards because a proton is not an antiparticle. It's absolutely fine. Now we've got an interaction here. We've got two particles, so there must be some form of boson involved. So we pop that in there. We make it a wee bit smaller at this stage. And because the W minus boson does exist for a little period of time, it should be slightly slanty, but pretty much across the ways is grand. because it exists for a ridiculously tiny period of time. This is my W minus boson. And out of my W minus boson, I'm going to get 2 further particles. Right? And this is my electron and my electron anti-neutrino, which I've had the sense to do over there. Okay, now the proton had to go this way because of conservation of momentum. Because of the fact that the electron is changing its position in this direction, and I've got the electron anti-neutrino going this direction as well, the proton must go in the opposite direction because the neutron was not changing position in the first place. So there is a conservation of momentum involved there. And this is a Feynman diagram. And this is how it looks for beta decay. Now we can get ourselves super duper fancy by doing the following. We can actually just, instead of having neutron and proton, we can replace that with our quark. That it is a down quark, and then that becomes an up quark. So our down becomes an up, and everything else remains the same here. And if you want to be ultra fancy, you can do another couple of arrows in here as well. And you can express the entire system. That you can have down, down. I can grab this one and get it in the right place. Come on. Send that back and I want to grab that. There we go. There we go. And I can express the entire neutron as a system of its 3 quarks. That we have the up, down, down, that is the neutron, becoming the up, down, up, that is our proton at the end. And this is beta decay in a nutshell as a Feynman diagram. Does that make sense? Okay, Nathaniel, Mr. Dunn is absolutely grand. Actually, I was chatting to him earlier this week, but nice of you to ask. I'll pass on your concerns for him. He's in good form. You know, well, as good as you can be living in Claudia. It's not exactly a metropolis, but it's all the world to me. Okay, so this is Feynman diagrams. Time, y-axis, position, x-axis. Now, I did say we'd take a look at beta positive decay just for fun. So let's just do that. Beta positive decay is in fact the exact opposite way around. That in beta positive decay, you've almost certainly never heard of it if you're still at A level, is that you have the opposite situation happens. That your proton, your up, up, down, becomes a neutron. All right. Now that's a bit of an issue because you've got a charge problem here. So we'll sort this out using our newly found fantastic skills. And this will be our last thing. So Q, B, and L are what we want here. Okay, so our charge on our proton is, of course, +1. And our charge on our neutron is 0. So that's a problem. Baryon number is 1. And our neutron is 1. That's fine. 3/3 altogether. Lepton number is 0, 0, and then don't know. Thingamies. Okay, so our biggest problem here is we have a charge problem. So we know that at least one of these particles is going to have a +1 charge. Okay, that has to be true because I've got 1 plus charge. That has to go to 0 and +1. Okay, we know that we can't create baryons because we've got our baryon number sorted out here, though I could possibly create a baryon-antibaryon pair. That would be an issue though because I wouldn't have enough mass to do that. Okay, I wouldn't have enough energy certainly to create another 3 quarks and 3 antiquarks out of that. So baryons are out of the question here. Leptons are in, but if I'm going to create leptons, I'll need a lepton-anti-lepton pair, which I can do because their masses are much smaller. So I know that I'm going to have sort of a lepton number of +1 and -1 required. Okay, so essentially I need a lepton with +1 charge. And that is only going to be the positron. Okay, it has a +1 charge and a lepton number of -1. Okay, so I can score these two off my list. and I can say that this is a positron, E+. All right. So that then leaves me with my last particle having to have a charge of 0, because I've sorted this line out, and a lepton number of +1. And therefore, what that has to be, with a charge of 0 and a lepton number of +1, is my electron neutrino. Okay, which is a little bit easier to write, so we can write that in here. So neutrino, and then a subscript E. I said it was easier to write, I lied, it wasn't. And that's beta plus decay. Okay, where you get a positron out, and this happens surprisingly frequently, actually. Job's a good one. And the mechanism is pretty much exactly the same, that except here we have the up, up, down becomes an up, down, down, and the boson responsible is a W+. All right, so that's it. That's it. You understand beta decay. You understand it by quark model. You hopefully understand that Q, B, and L must be conserved in any reaction. So we're done. You have somehow managed to complete A-level physics despite the coronavirus pandemic stealing you from my clutches and robbing me of your company for the last few months. Okay, so for all of you watching who are students of mine, who have been students of mine, it has been a wonderful pleasure to teach you. I feel massively cheated that I didn't get to teach you all the way up to the end and watch you go through the horrors and stresses of doing your exams, and more importantly, seeing you come out with the successes at the other side and seeing the victories that would be won. It has been my great honor and my great privilege to teach you. I hope you all keep in contact, and please, 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 no matter what you do, no matter where you go in your life, there's a few things that you need to remember. Always, always, always go where the evidence leads you. Be empirical. Don't get conned. Go, what's your theory? Where's your evidence? How do we work this out? Does that make sense? Right. Secondly, physics is for everyone. It's not a massive kind of unpenetrable mess of stuff. Use your physics knowledge in day-to-day life. It hopefully has changed how you look at the world. And the final thing, the most important thing that you must remember after 7 years through my hands, is that of course physics rocks. It's true.